While I was at that same workshop in Portland, I also had a chance to sit down with one of our invited speakers, Huang, to talk about her path to working in astrochemistry. Well, thanks for chatting with us, Jane. So what I wanted to start off and ask you is, how did you get interested in astrochemistry to begin with?
Well, so when I started college, I wasn't exactly sure what I wanted to do. There were a few different things I was interested in. I was taking physics classes. I wanted to take chemistry classes. I started working with this astronomy professor over the summer on extragalactic astronomy. Nothing to do, strictly speaking, with astrochemistry, but I was really interested in astronomical spectroscopy because I thought it was just really cool that you can just look at how much light something is getting at different wavelengths and figure out, like a detective, what you are seeing.
Yeah.
And then I learned about something called diffuse interstellar bands, and I just thought it was wild that there was like all this chemistry happening in space that's very different from the chemistry that we're used to in everyday life, because you're taught all these rules in high school, and then the astronomers tell you need to forget about those rules.
Absolutely, yeah.
So then, in my senior year, I started working with an astrochemist, Takeshi Oka, probably most famous for his work on H3+.
Which violates those rules we were taught.
Exactly. H3+ is a molecular ion, and certainly something you never learn about in high school chemistry.
No.
So I thought it was really interesting what he did, and so I wanted to continue studying astrochemistry in grad school. And so, at the time there weren't that many astrochemists working at the faculty level in the US, so that led to a very short list of people that I reached out to talk to about whether they were taking students, what kinds of projects that were possible to work on in a PhD. And one thing I kept hearing over and over again is, ALMA is the future. ALMA is the future. So ALMA was a radio telescope that was constructed shortly before I started grad school. Most powerful radio telescope in the world. And one of the big things that it was designed to do was to study the chemistry of what are called protoplanetary disks. So these are the disks of gas, dust, and ice around young stars. So I went to do my PhD at Harvard, which is one of the foremost centers for protoplanetary disk studies. And so there I was studying both the physical structure of protoplanetary disks and their composition using ALMA.
Very cool. So, and correct me if I'm wrong, but Harvard is a unique environment because you have a mix of faculty from the actual astronomy and chemistry departments, but also permanent research staff at the CFA, the Center for Astrophysics, right? And so that seems a little different from the structure that a lot of folks think of when they go to graduate school, where they're just working with one PI. So did you get to interact with the research staff? How do they influence the way that you did your research, if at all? You tell us a little bit about that environment.
Yeah, so you're right that it's a very unique environment. In fact, the astronomers at Harvard are outnumbered by the astronomers at the Smithsonian Astrophysical Observatory. So we had something called a disk group, which was led by a mixture of Harvard and Smithsonian people, and I feel fortunate that I was able to be able to learn from the expertise of so many different people. So the CFA is so big that it's impossible to know everyone. It's like years later, I will meet people who are at the CFA at the same time as me, and we never spoke to each other and even necessarily knew each other existed. But then the advantage of being at someplace so big is that it feels like there's an expert in almost any aspect of astronomy that you would want to be able to ask about.
That seems, it seems like a great thing when you're working on what is increasingly mandatory interdisciplinary science, right? Especially when you get into things at scales that protoplanetary disks sort of bridge from clouds all the way down to planets, right?
Right.
It's an interesting mix. Yeah. Okay, so PhD in protoplanetary disks. Presumably you kept working on that in your postdoc?
Yes, I did. So then I moved on to University of Michigan, which is another focal point of protoplanetary disk research in the US. And so I continued doing things with ALMA, but then started branching out more, collaborating with people working at other wavelengths. working with telescopes such as VLT Sphere. And then at Michigan, I started thinking more about the environmental context of protoplanetary disks. They're not just these islands of planet formation, but they're affected by their surroundings.
Very cool. So that's, you're talking about, and correct me if I'm wrong, but you showed images where you have material infalling onto the disk from its surrounding cloud, and trying to look at the way that the initial cloud conditions affect the eventual composition of the disk, or something else than that?
Well, not necessarily the initial cloud conditions, but just the fact that there's external material seemingly being transferred to disks.
I see.
Another aspect that I've been looking at recently is how disks are affected by radiation from nearby massive stars.
Okay, cool. So we talked a few podcasts ago about how the surfaces of protoplanetary disks actually are kind of like a PDR, photon-dominated region, because of the radiation from the central star. But in your case, your disks are almost like super PDRs because they're being blasted not just by the central star, but by the surrounding additional protostars.
To be determined. So
Okay.
for those disks so far, I've only looked at dust continuum, which is just telling us what the solids are doing in the disk midplane, the dense region that's more protected from radiation.
Okay.
But we're getting new ALMA and JWST observations to look at the gas. So that being said, the disks I'm looking at are not as extreme as some of the other disks that people have looked at. So there have been published studies over the last couple of years of a couple of disks in the Orion star forming region, where they do see these molecules that you would only expect if you have these really high levels of ultraviolet radiation. So, and an open question is, well, how commonly should we see these across different kinds of disk environments?
Yeah, that's an interesting question. So this is presumably where you're taking your research group now, because you're faculty at Columbia and have been for 5 years?
No, a little bit over 2.
A little bit over 2. Wow. Okay, time flies.
Or doesn't.
Well, it depends. Okay, so a little over 2 years then. So is this how the sort of questions that you're building up your research group to try to tackle? Do you have different areas of investigation you're also looking at?
Yeah, I mean, I would say that my big focus in the near future is going to be on disk environments, but the other aspect that I've been thinking about also is how disks change with age, and that intersection with those environmental effects, because the environments are also not constant with time.
Yeah, that's a great point. So I guess naively, we think about planet formation in stages where you start with a cloud, it collapses to a core, then a disk forms, but it's still embedded in its cloud. And then the cloud starts to dissipate at some point surrounding the disk, right? And this is, you're trying to tie that timeline to cloud change and dissipation and the cessation of accretion or changing the amount of accretion onto the disk to observable properties and figuring out what it's going to do as the disk evolves?
Yeah, basically. I mean, one of the things that we still don't know for sure is when exactly does planet formation start.
Oh, okay.
And so we know that that the disk environment is changing. Like you said, the disk is, there has tons of material falling onto it, and then eventually it'll dissipate. And then from the radiation side, disks are moving around in the cluster. They're not just always parked at the same location relative to the star. So we need to understand, when does planet formation start and how long does that take place, and how does that compare to all the other external processes going on?
Very cool. Okay, I have probably a naive question, but I hadn't considered the fact that the disk system itself will move relative to some of the other, say, massive stars in the region. Does it move enough in the lifetime of the disk to change like the irradiation angle onto the disk itself?
So that's one of the questions that's one of the open questions. I mean, there's something called the propelid problem,
okay.
So propelids are like these disks where you can see in the images there's material being blasted away.
Okay.
Sorry, it's a propid lifetime problem.
Okay.
And if you measure how much mass they're losing, it seems like the proplyds shouldn't live for very long, but you're seeing them at an age of around 1 million years, maybe a couple million years. And so there have been different ideas for why that could happen, and one of them could just be that the irradiation levels have changed enough over time that we're happening to catch them when they're losing a lot of mass, but maybe at other times in their life they're better shielded from the radiation for different reasons.
Okay, a variable mass loss rate. Interesting. All right, so one last question for you. What do you think is the most exciting discovery you think might happen the next, say, 5 to 10 years as we're here at the ALMA WSU and NGVLA conference, as these capabilities start coming online? What do you think new frontiers are going to be opened in research for protoplanetary disks?
Well, so to some extent, this has already been done a bit, like the surface has been scratched, which is studying something called circumplanetary disks. So protoplanetary disks, despite what the name sounds like, are the disks around young stars. And with astronomy, sometimes it's turtles all the way down. So the young planets also can have little disks around them. Now, there's been one detected for sure, and some candidates, and then some analogs around brown dwarfs, other substellar objects. There was a recent study, I think, looking at using JWST to study the disk around a substellar companion. And I think with the better resolution sensitivity of future instruments, it would be interesting to know, like, what are these circumplanetary disks' physical and chemical properties in much better detail than we have now.
Awesome. Is it, again, a possibly naive question, would you expect that it's possible that you would observe one of these circumplanetary disks and find that its composition varies dramatically from the ring, the radius, material in the radius that it occupies in the protoplanetary disk?
So if I remember correctly, the recent study of the substellar companion disk basically did find that. But of course, there's no guarantee that that system formed in the same way as the less massive objects. Okay. So we expect that the formation process should also impact the disk composition. But that in and of itself would be an interesting result.
Really cool. Would that be a way to track potential migration of these planets as they move from one location to the other, or not?
I think the naive answer is yes, but then the sort of always like more cautious answer is it depends.
Fair enough, fair enough. All right, well, thanks so much for taking the time to chat with us today.
Okay, well, thank you for having me on.